power density of solar radiation at the top of the atmosphere is about 340 watt per square meters. The world total primary energy supply was a bit more than 13 billion tons of oil equivalent in 2013. If we spread this amount all over the Earth's surface, we obtain a number that is 10,000 times smaller than the top of the atmosphere's solar radiation. But what happens to short-wavelength solar radiation as it travels through the atmosphere? Which are the main physical mechanisms that are involved? When electromagnetic radiation hits matter, it undergoes different phenomena, including reflection, refraction, scattering, and absorption. The type of interaction depends on the optical properties of the receiver, which are generally wavelength dependent, and its molecular structure. The atmosphere of the Earth makes no exception. The mixture of constituent gases and vapors reflects a significant portion of the incoming solar radiation back to the outer space. The remainder is then either absorbed by the atmosphere or transmitted toward the Earth's surface. In figure, the spectrum of the solar radiation is shown. The visible spectrum, that is between 400 and 700 nanometers, accounts for slightly less than half of the Sun's total energy. The atmosphere and the ground emit instead most of the energy in the infrared region. The most abundant gases in the atmosphere, which are oxygen and nitrogen, are almost transparent to both solar and infrared radiation. Other gases, such as water vapor, carbon dioxide, and methane, even if present in smaller amounts within the atmosphere, can absorb thermal infrared energy. For this reason, they are known as greenhouse gases. We will see that greenhouse gases play a key role in regulating the temperature of the surface of the Earth and the atmosphere. The greenhouse effect is indeed the key Sun-atmosphere-Earth interaction that has been changing the Earth's climate since the last 5 billion years. Let's analyze how does it work. The cartoon shows the main energy flows exchanged between the Sun and the Earth. The atmosphere interaction with both short-wavelength solar radiation and the Earth's long-wavelength thermal emission is taken into account. The left side of the figure shows how about 30% of the incoming radiation is reflected back to the outer space by either the atmosphere and the surface of the Earth. The atmosphere and the Earth's surface absorb respectively 20% and 50% of the remainder. The right side of the cartoon is slightly more complex. It shows several arrows, each of them denoting a different radiative contribution. Especially, the upward thermal radiation from the Earth's surface is shown, as well as both upward and downward long-wavelength radiation from the atmosphere. Looking at the overall picture, what is important to observe is that the incoming solar power density equals the overall outgoing terms. This is consistent with the first law of thermodynamics. The fulfillment of this radiative balance determines the equilibrium temperatures of the Earth's surface and the atmosphere. These values are such to instantaneously match the incoming with the outgoing energy flows. To better understand the previous cartoon, let's build together the Sun-atmosphere-Earth radiative equilibrium model. The goal is to calculate the temperature of the Earth's surface. This model is somewhat more complex than the previous one, in which only the Sun-Earth radiative equilibrium was included. In the model, the atmosphere is described as a single semi-transparent layer that is placed between the Earth and the Sun. This layer has different absorption coefficients in the short wavelength and long wavelength radiation ranges. The detailed model considers two control volumes which represent the atmosphere and the surface of the Earth respectively. These two systems exchange energy between each other and with the external environment, the outer space. In figure, the exchanged energy flows are shown with blue and red arrows that refer respectively to short and long wavelength radiation. Energy transfers considered within the model has been defined as fluxes F1 through F8 as shown in figure. The energy balance for the two systems include all incoming and outgoing energy flows through the control surfaces. The solution of this system of equations allows one to calculate the atmosphere and the Earth surface temperatures. Realistic values of optical properties result in a surface temperature of 15 degrees Celsius. Despite the simplistic model, this is actually a very accurate estimate of the average temperature of the Earth's surface, which is 14.5 degrees Celsius. It is worthwhile to remind that by neglecting the atmospheric contribution, the result was the unrealistic and rather crisp temperature of minus 18 degrees Celsius. More accurate estimates could be obtained with the use of more complex models. For example, convection phenomena should be taken into account to describe spatial temperature gradients in the atmosphere. Nonetheless, a simple calculation of radiative equilibrium like the one we have just carried out is useful to understand the physics of the energy balance of our planet and the potential effects on climate change. Any natural or anthropogenic alteration of the atmosphere radiative properties could be responsible of long-term variation of the temperature of the surface of the Earth. In figure, it is shown that the Eiger is the absorption coefficient for the long wavelength radiation of the atmospheric layer. The Eiger is the Earth's temperature. These results show altogether the importance of the atmosphere in maintaining our planet warm. Indeed, the actual atmosphere composition is such to maintain an optimal radiative equilibrium condition that allows life for humankind on Earth.